Let's start again. So, good afternoon, everyone. Welcome again to this edition of the NITheCS Colloquium. I'm very happy to introduce to you today Professor Andronikos Paliathanasis. I hope I got it right. Andronikos has an affiliation with Stellenbosch University and with NITheCS, yeah, but his main affiliation is with the Catholic University of the North in Chile. Yeah, Andronikos did his PhD at University of Athens in mathematical physics, yeah, which is very good. Yeah, and is a very prolific researcher, yeah, with hundreds and hundreds of papers. and today he will speak about an equation to rule it all, yeah, and some
about Hobbiton.
yes, probably. Yeah. So, Andronikos, please, over to you.
Thank you for the invitation also and for being here. It's really a pleasure. I want to thank Professor Petruccioni and, of course, the Deputy Vice Chancellor, Professor Moyo, who is a colleague for many years. And I'm really happy that presenting this work here to you, since it is a result that came after a mini workshop that took place in Stellenbosch almost 18 months before. It was October of 23, if I remember correct. And during the discussions we had this period in the workshop, we were able to express some ideas that I had from the past, and I was discussing with Professor Moyo and Professor Peter Leeds. So the title is, it's One Equation to Rule Them All. I'm sure that you recognize it from Tolkien, from the One Ring to Rule Them All. So why is that? I will present you that set of models which are important in gravitational physics are described just by one equation. All of them, which are nonlinear, can be described, and their solution actually can be described by a very simple equation. In modern science, actually, modern science is the science changed by two perspectives. Firstly, we have the Francis Bacon, who introduced, who is the empirical, who says that we understand the knowledge through experiments, and as well as we explore the experiment world, we understand the world much better. And then we have the second school, with the school of Descartes, that states that there should be a unique truth for everything. So physics it's a little different in terms of the rest of the applied mathematics theories. In physics, we start from a variational principle, we start from a truth, and surprisingly, that works for general relativity. We can do predictions and we can understand the world from before. So that's why having a common feature, it's really interesting. So I will try to be less technically, and my presentation, as I told you, this work started after October 23, so this work was published recently in this series of studies. So what was the idea? What was the motivation, actually? Either when I was a student and a graduate student having to work with nonlinear PDEs or ODEs, one of the main books that I studied, it was probably the first book on differential equations, which wasn't in Greek, actually, in English literature. So it was the book of Ascot. Ascot, in the preface, starts with very nice phrase that fall back on numerical techniques savor somewhat of breaking a door with a hammer when one could with a little trouble find the key. So sometimes, either when we have a very bad equation, very nonlinear, and we see it, we say, okay, I will solve it numerically. Sometimes when we apply simple techniques, we can solve it. So using numerical techniques doesn't always tell you that you have the solution. Doesn't always give you the full information for a differential equation or for the physics or the model behind it. And while nowadays we have strong computers, in the past they didn't, we are lucky on that. We have AI, we have machine learning, we have neural networks to solve difficult problems. Always is essential to try to find an analytic expression. for many ways. I mean, in terms of environment, for instance, you have heard data recently how costly it is to say thank you to ChatGPT. It costs a lot. I mean, it's usually we solve something numerically, but we don't think when we do it how costly it is. It needs energy, it needs power. On the other hand, when we have models with exact solutions, either which are not exactly the real solution of the problem, or they are asymptotic solutions, we give information to the solver like, look, this is the solution space, this is the parametric space, move there, but the real solution will be around these stationary points. So giving information from before, it is essential either to reduce the computational time for the numerical simulator. So I will talk about degradability and I will talk about degradable dynamical systems. And an essential feature for this degradable system is the concept of symmetries. Symmetries are really essential, and our world is based on that. And of course, and when we break them, things are getting more interesting. But I will stay on the basic one. So how I define a solution of differential equation for a system of differential equation? Well, there are various definitions, and the most common definition is to have a set of explicit functions describing the variation of the dependent variables with the dependent variables. So we call this solution as closed form solutions. For instance, the solution for the oscillator expressed in cosinus and sinus function, it is a closed form solution. However, in other solutions, the existence of a sufficient number of independent explicit first integrals and invariant. So either if you cannot write the solution in closed form, you can write in terms of integrals. And also the existence of a sufficient number of explicit transformations which permits the reduction of the system into a set of algebraic differential equations. So these are three different definitions for the definition of the solution. And of course, when we have explicit functions or when we construct an explicit function to describe solutions, it's much nicer and easier to work. Now, why exact solutions are important? And in gravitational physics, as I told you before, in gravitational physics, for instance, we start from an action principle. We start what we call of the Einstein-Hilbert action, which provides the Einstein field equations. And then by assuming different constructions for the physical space, we can solve them and find exact solutions. One of the first known exact solutions that was determined was the solution of the Schwarzschild, which described a black hole. So mathematically, a black hole was constructed, but it was observed much years later. So as you can see, exact solutions allow for the precise modeling of gravitational fields and the space-time structure. Some solutions which are important, like the Schwarzschild or the Kerr or the black holes. And also we have exact solutions in order to understand the evolution of the universe during the inflation, or to understand the dark energy model. And nowadays, there's a discussion about deviation from general relativity. So we use the exact solutions to understand how far we can go from general relativity. And exact solutions serve as reference points for evaluating numerical simulation and approximation techniques. Verify the accuracy of the approximation, especially near singularities. The mixed master universe, which was a very famous solution description for the Big Bang singularity in the 60s, is approximately near the singularity by the Kastner approximation, which is an exact solution. And of course, as I mentioned before, to reduce the necessary computing power, the perturbations or in the data analysis. So these are some exact solutions which are of real special interest in gravitational physics. In cosmology, we have the de Sitter universe or the Lambda-CDM universe. We have anisotropic and homogeneous exact solutions like the Kastner, Bianchi 3, Bianchi 7, and others. And of course, we have inhomogeneous exact solutions, which play a significant role in inhomogeneous cosmology for the analytical description of the of the anisotropies and the homogeneities, and of course the black hole solutions, the exact black hole solutions that we have. I just mentioned a few of them. So, yeah, one of the main results I will on the symmetry analysis. Actually, the symmetry analysis was established by Sophus Lee in the end of the 19th century during the period I think he spent in the prison. He was arrested for a month during the Prussian-French War. So, a significant finding of Lee's theory is the geometric linearization of differential equations. So nonlinear differential equations can be expressed and can be linearized through canonical transformations. Sophus Lee, on his first book, published the following theorem for second-order differential equations, that if a second-order differential equations of this form admits 8 Lipon symmetries which form this Lie algebra, then there exists a transformation that can bring the equation to the form of the free particle, to the form of the equation of this form. Why this is important? Except from solving equations, let's see it from the point of view of physics. We have how we do physics, either when we are in the physics lab in the undergraduate level. For instance, if we want to measure the gravitational constant G, what we do is that we allow things to fall down, for instance, or we take a pendulum, much better. It's much better experiment with less error. We have a pendulum, and we make a table, and in the table we have its position in terms of time. So we make a plot of the data that we have, and from the data we interpret a function that explains the data. For the pendulum, it will be sinus or a cosine. For the free particle, it will be a straight line. Both equations are maximally symmetric, are linear, of course, the oscillator, and the oscillator I can write it in terms of the free particle. That means that there exists one-to-one transformation that I can relate the oscillator to the free particle. Is this physically? No, I observe something different. But the solution space is the same. I can map the one solution to another. How can I go back? What if how I measure the time? I measure the time with a clock. I measure the distance with a meter. What if my organs my clock weren't linear? It was a nonlinear clock, or my meter was nonlinear. Then the data that I will have from the oscillator will give me a straight line in a plot xy, graph x. So that is the interpretation that we can see in physics, or how we can relate the result. And the important in this is that the transformation is, well, it's local, it's hold for any period of time. So for instance, first interpretation, the first application of Sophus Lee theory is the following, that these three equations, which are, the first one is the oscillator, and actually it's not an oscillator, since this can be an oscillator, it can be a pendulum with the time-dependent mass. This nonlinear equation with a damp, and this ugly nonlinear differential, when you see it, you say that it's awful and probably does not have a solution. I will solve it numerically. These three equations actually are the same, expressed in different coordinates and in different representations. These three equations, and not only these, they share the same common algebra. They share the same symmetries in different representations. And actually, there exists one-to-one transformation that I can write the third one to the first, or to the second, or in terms of the free particle. For instance, for the oscillator, how I do this, if this is a constant, I can write it in this form by making this change of variables. And what this Penn-Leveins equation can be linearized by applying this transformation. So by using this, the property of Sophus Lee theorem, I can solve these equations in a very simple form. And their solutions can be expressed in terms of the linear functions. However, another equation of very special interesting is the Markov equation. The Markov equation, also known as the Markov-Pine equations, Ermakov presented in the end of the 19th century. In the middle of the 50s, Piney presented solution. The Ermakov-Piney equation, it is a second-order differential equation, nonlinear, with a linear coefficient term omega t. This is a time-dependent mass, and this nonlinear power law term. And it is invariant actually by the SL2R algebra. So it's not maximally symmetric. But the solution of it, according to Piney, is the following, given by the following formula, where x1 and x2 are the two solutions for the linear equation. Piney on his paper didn't present the solution, how he derived the solution. It is one of the nice mathematical papers that someone present the equation and the solution, and without any proof. The proof is that you replace and you do it. So that was actually my starting point when I left Stellenbosch. And I was thinking, I know this term. We know that. It's in any classical textbook of analytic mechanics or of Newtonian mechanics. It came from central forces. So I say, okay, why I don't consider another system? This one. This one is a two-dimensional system of second-order equation. Right. I increase the dimensionality, but at the same time, I introduce a conservation law. And this is nothing else than the conservation law of angular momentum. So instead to see the system as one equation, I say I will see it as a two equation. Like this. But this is just a central force system expressed in polar coordinates. Can I go in Cartesians? Yes. We can apply the transformation going from polar to Cartesians, and the system is expressed by this. This two-dimensional system is actually maximally symmetric. That means the SL4R algebra is an extension of Sophocles' theorem in higher dimensions, and this can be expressed in terms of the free particle, applying the transformation I showed you before. So after the application of the conservation law, in order to reduce the original system, all these symmetries, which are 15 in number, are getting lost, are getting non-local actually, and only 3 remain local, this one which form the SL2R algebra. So by using the lift, we can construct new dynamical systems which are linearizable. So we can apply a method which is called Eisenhart-Duval lift to construct equivalent systems with equivalent solution and can be linearized. That's the approach I would like to show you here. So I will try to be less technical. I couldn't avoid it. I'm sorry for that. And I will show you systems Hamiltonian mechanics, simple systems of this form. So we start from this second order differential equations, other central force. And since I assume that I have, which given by this potential function and described by this Hamiltonian. So we know that when the potential is the oscillator, the differential equation is linear and maximally symmetric, and there are no other potentials or functions f which tell us that this equation is maximally symmetric. But can I construct other potentials, other functions f, in order these two can be linearizable by using the lift? That was my question. So the method I apply is the Jacobi and the Eisenhart lift. And I apply both of them, mainly the Eisenhart lift, which are two distinct methods for the geometric representation of the dynamical system. Based on the same spirit with Einstein, we try to absorb the forces in terms of geometry, and while we have a dynamical system moving under the action of a force, we try to see it as an equivalent system of geodesic equations in a non-flat geometry. So in the Eisenhart lift, what we are doing is that we increase the dimensionality of the system by introducing new dependent variables, but at the same time introducing conservation laws necessary to reduce to the original system. So we introduce a kinetic metric, an extended kinetic metric, which is characterized by at least one isometry related to the Noetherian conservation law for the geodesic equations. So that is more or less the approach. And in order to do it for the Hamiltonian I presented you before, for this one, what I did is, what we are doing is like, we have, okay, I have one here. This constant one, I can introduce it as a momentum, Pz. It's a new dimensionality. And the momentum Pz, it's a conservation law. And I can say that I recover the original system when A over 2 Pz squared equal to 1. Now, this Hamiltonian describes the set of geodesic equations in a manifold with line element, this one, in a Riemann manifold with this one. And this is known as the Eisenhart metric. The geodesic equations are of second order, and the Hamiltonian equations are this one. As you can see, this is the conservation law. And by replacing the conservation law, we recover to the original system. So if we know the solution of this, we can construct the solution of before. And the constraints are the following. Now, for this potential, the extended like element, it takes this simple form, which is nothing else what we saw before, the flat space expressed in polar coordinates. So going from polar to Cartesian coordinates by this transformation, we can express this line element to this, and the equation of motions, which are these, 2 times of the free particle. Indeed, this approach allows us to construct non-local conservation laws, so we can write the Ermakov-Pino equation from the equation of the free particle. So we start from the free particle, and we apply a non-local conservation, a non-local transformation, a non-canonical transformation, then, or this, then we end to this equation, which is a non-linear equation. So this linearization is achieved by non-local symmetries in the level that the equation exists, or from local symmetries in the previous level before I applied the transformation in the lift. So at this point, also it's also to mention that if I introduce the omega sigma here, the omega t, this property holds, and this can be absorbed and removed by the system by applying this change variable. Now, some basic geometric definitions are the following. Since the result and the approach can be held for any dimension, and but for Riemannian geometries at least here. So if the metric tensors are, I have 2 spaces with metric tensor G and G bar, then they are conformally related if and only if there exists a coordinate systems that I can express the one in terms of the other. So if Gij is a conformally flat space, then it means that this one can be expressed in terms of a flat space as here. And another definition is like functions which are L and L bar, which describe the geodesic equations of conformally metrics. Now, the Euler-Lagrange equations for 2 conformal Lagrangians transform covariantly under the conformal transformation related to the Lagrangian if and only if the Hamiltonian vanishes. How we interpret that? We know that geodesic equations which have energy 0, we call them null geodesics, or geodesics we describe the light in gravitational physics. So the light, the evolution of the light is independent of the conformal transformation. So that means that for conformally flat spaces, there exists a transformation that the geodesic equations for the light can be expressed in terms of the free particle for the flat space. So before for this Hamiltonian for the H1 plus 1, the question is for a general potential when this can be flat. And in order this line, 2-dimensional line element to be flat, we calculated its scalar, and we found that its scalar is flat if and only if this is a potential I presented before. But this is not the unique lift. This is not the unique extension of the geometry that we can do. There can be many extensions. So another extension that has been applied is called the Lorentz extension. In this extension, we introduce two new dimensions, and there are two new conservation laws at least, and the original system is recovered by these constraints. And this three-dimensional geometry now is flat if and only if, or conformally flat, if and only if the potential is given by this equation. That means it's the oscillator term. But we can extend it more. And that allows us to construct new potentials and new functions. So if I introduce another one kind of extended Hamiltonian, we can go further and we can construct new potentials. Or furthermore, we can construct the Morse potential. So the Morse potential, for instance, which is a nonlinear potential, and it's not maximal symmetric, can be linearized somehow. And for instance, if you take this Hamiltonian, which is a Hamiltonian which describes the Morse potential, and if you apply this change of variables, then you start from here, you end it here in the linear form. Now, but that was one way, and the other way is to use when this can be conformally flat. And since I have a one-dimensional system with one potential, I can reduce it to a two-dimensional system, 1 plus 1. But two-dimensional spaces are always conformally flat by definition. That means that if the energy is 0, and how can I put the energy 0 in a Hamiltonian system? Easily, I can absorb it inside the potential. I can take the energy inside the potential and make the Poincare space to have volume 0. So in this case, if I apply this, I have this extended line element, I can apply a change of variables and write it in the form of the conformally flat space. So easily, this Hamiltonian ridge of this describes the same system as this one, which is nothing else than the conformally flat space. And the equations of motions are linearizable for any potential term. And of course, if I want to calculate the symmetry, since now I don't have for this SL4R, I have infinity symmetries given by the infinity dimensionally the conformal algebra, which plays an important role in conformality theory. So I wanted to present you some basic results which were applied in analytic mechanics, and now we can apply them in gravitational physics to understand how these tools can be applied in Einstein field equations. So an important characteristic for the models that I will talk is the mini superspace description. In the mini superspace description, we see the evolution of the Einstein field equations, the dependent parameters for the Einstein field equations to be involved as point particles and describe it and to be described by a Lagrangian function of a point-like function in a geometry which is called mini superspace under the action of a potential term. In the mini superspace description, the gravitational field equations can be expressed easily in a very simple manner, which give us important information for the degrees of freedom. And we can apply the mathematical tools, either the one that I present now, but we can apply all the tools of analytic mechanics to understand the evolution and the solution of the model. However, in the equivalent Hamiltonian formulation through the use of the Dirac-Bergman algorithm allows for the distinction of the true degrees of freedom for the reduced gravitational system, which is useful, especially in case where the generic Hamiltonian formalism of general relativity. And it was one of the first approaches to reach the problem of quantum gravity through the Wheeler-DeWitt equation, where actually the Wheeler-DeWitt equation in the mini superspace description is reduced to a single equation, analogous to the Schrödinger equation. Now, I will be a little simple. So, for instance, consider the statical spherical symmetric spacetime, where actually here usually you will see this to be R square only, but without loss of generality, we can write it in this form. So there are three scale factors here, A, N, and B. But only two are essential. And R, actually, it's a lapse function, and we can set it whatever we want. But however, when we put this to be R, we determine the N. So only two of them are essential. And only two of them are determined by the Einstein field equation. Now, the solution of this, in the case of the vacuum, with or without cosmological constant, is the Schwarzschild-de Sitter solution, which is non-solution by the Schwarzschild was found by Schwarzschild during the First World War, is this solution. However, the field equations, I describe it, express it like that, I describe it by the following point-like Lagrangian. We have a mini superspace description here, and that's important. So as you can see, parameter A and B are given by a Lagrangian of this form, and are which, as you can see, there is a kinetic energy term here, and is the potential term. The potential term is related to the cosmological constant lambda, and it's related to the curvature of three-dimensional hypersurface. But the kinetic term, as you can see, there is no any first derivative of n. That's why n can be absorbed due to the constraint. And A and B provide second-order differential equation. So we can write a Hamiltonian expression as before, and we can introduce the equivalent Hamiltonian function in the Eisenhart-Duval lift as this form. So where I had the potential, I made the constant to be a momentum. And that momentum, it's constrained with the value 1 to recover the original system. Now we have an extended mini superspace. We have a mini superspace of dimensional 3. And this extended mini superspace has a property. We calculate the Cotton-Yoke tensor, and the Cotton-Yoke tensor tells us that it has 0 components. It's always 0. That means that this mini superspace is conformally flat. So there exists a change of variables, was found to be this one, and the mini superspace takes this. And the Einstein field equations for the Schwarzschild spacetime, which were really nonlinear, can be written in the linear form of the free particle for the three dimensions, with this constraint, to recover before, with or without the cosmological constant. That means that I can start from the solution. As you can see, the cosmological constant is inside the transformation. So I can start from the solution of this free particle and apply the transformation and recover the solution for the Schwarzschild or for the Schwarzschild-de Sitter. Or I can start from the solution of the Schwarzschild and recover the solution for the Schwarzschild-de Sitter, or the Schwarzschild-de Sitter for another value for the cosmological constant. But the interesting thing is that this property exists either when we introduce charge. In the Reisner-Nordstrom black hole. In the Reisner-Nordstrom black hole, we have the mini superspace description of the Schwarzschild plus an additional term related to the charge. So apply the same approach as before. Here we don't have the cosmological constant, but it plays no role. As before, we see that this four-dimensional mini superspace now, a set of geodesic equations, are formally flat, have a wild tensor to be 0. That means that there exists a transformation, so I don't present it here, that I can write these four equations in terms of the free particle of a 4-dimension. So either if I start from a space, from the Schwarzschild, either if I introduce in the vacuum of the static spherical symmetric spacetime cosmological constant or charge, at the end, the solution space is given by the free particle. But that property does not hold only for the Schwarzschild. It holds also for a majority of gravitational models of exact solutions that we already know. And for some that we didn't know in modified theories of gravity. For instance, in general relativity, the vacuum solutions in some LRS Bianchi models are exactly linearizable as before. But we can go to study the field equations in homogeneous models, and indeed, the Jacobi solution with or without cosmological constant have this property to be linearizable. And if we go in Freeman-Robinson-Walker, we introduce or in where we introduce scalar fields to describe either the inflation or the late universe. And for instance, for the exponential potential, the field equations can be linearizable and described also from the field particle. That also holds, and where we introduce different mechanisms which give interaction between the dark matter or the dark energy, like the Hamiltonian mechanism, or for other ideal gas. And of course, in modified theories of gravity, where we have new degrees of freedom here. This property holds for some models. So it's like we have the majority of the solutions, of the exact solutions that we have, can be connected in an attribute in one model, in the terms of the free particle, which for me is the one equation that rule them all, describe them all. Why this is happening? Is there a common feature between them? Yes, there is a common property here. All this set of differential equations admit a common subalgebra. They are invariant under this specific subalgebra. And that was the heat to understand. When I recognize this algebra easily, I can understand that the field equations can be linearizable in this form. So there is also a more general theorem that states that, which is independent of the Einstein field equations, but they are applied here and can be extended can be used also to extend this theorem to results of Einstein field equations or extensions like in Lovelock theories or other theories in higher dimensional spacetimes. So I have 5 minutes, and I want in these 5 minutes to show you a mechanism how I can use this approach to introduce cosmological constant or remove the cosmological constant or change the value of the cosmological constant in the very early stage of the universe when I am in the quantum level. So the first observation is that the lambda CDM model, which is the most simple model for the description of the acceleration of the universe, is described by the field equations are given by this mean superspace Lagrangian, where is the scale factor, lambda is a cosmological constant, and rho is the energy density for the cold dark matter. I don't include baryons or radiation here, I just stay simple. But we have the following observation. If you do the change of variable in the scale factor, the gravitational field equations are exactly the equations of the oscillator. And when lambda equals 0, we end with the equation for the free particle. So is there a transformation which relates the two solutions? We know from Sophus-Lie theory that I can express the solution for the oscillator using the solution of the free particle by applying canonical transformation. But when we are doing it here, due to this constraint, due to this n, this transformation is lost, does not hold anymore. However, can we find a transformation that does this? So yes, we did that by using the lift. And I write in an equivalent Hamiltonian to be of this form. So this equivalent Hamiltonian, which I apply the Hamiltonian, the Lorentz, Eisenhart-Lorentz lift, is this one, where omega plays the role of the cosmological constant. I just put it omega to relate it to the oscillatory term. So the equations of motion in terms of expressed in terms of Hamilton are given by this set, which are linear and easy to be described. So the lambda CDM model is recovered when the following set is true. Now, I consider an extended Hamiltonian for the CDM model. So let's just start for the CDM. As you can see, the CDM is this one, and the previous one was this one. So omega, when omega is 0, we recover the CDM. So this gives us the equations of motions for the free particle with cold dark matter without the cosmological constant. So we can quantize this in the simple way, in the usual way we quantize in classical quantum mechanics. And we can we can write the Wheeler-DeWitt equation which describes the wave function y, psi. So the wave function is given by this partial differential equation. How we solve it? Usually we solve with separation of variables, we construct solution. We don't have initial values, so that's a problem in quantum cosmology. We don't have boundary conditions, but we have to define them always later. But we know that this equation admits to observables, to operators, these operators which are the conservation laws for the momentum for the classical particle. So when we apply these operators, we calculate this wave function. And this wave function in the semi-classical limit give us that this is nothing else than the action for the cold dark matter model for the free particle. So we recover the classical solution. However, the Wheeler-DeWitt equation is invariant under another set of transformation, which is one of the many that it has, is this one. Expressed in non-canonical coordinates. So we apply a change of variable. In order to write it in a very nice form, we can write it from this ugly form like that. And express it like this, the Wheeler-DeWitt equation, simplified it like that. Do you recognize something? I have the previous one, which was this. I have this term of A, and I have here UV and M. But now I have the same term here. I have capital U, capital V, M. I have a new term here, which we see related to the cosmological constant. So now we define the new operators to be the PU, PV, and this gives us the new observables. And as you can see in the semi-classical limit of we recover the Hamilton-Jacobi equation, which is that of the lambda CDM universe. So the cold dark matter model and the lambda CDM universe in the lift, they share the same wave function. What is the truth? How we get the classical universe depends on the initial condition that we get. So we relax the initial condition, the initial value problem in the early stage of the universe. We can construct the lambda CDM universe from the cold dark matter. So the relaxation of the first class constraints can be used for the construction of differential equations and the construction of the classical model and for the description of the physics. Of course, that does not give necessary a solution for the fine-tuning model, a problem of the cosmological constant, but it can provide some mechanism which can be used for a solution for it. So I believe I was on time, and I want to thank you a lot.
Very much, Andronikos, for this interesting talk. Are there questions? Please. The microphone is coming.
Hi, thank you for the talk. I was wondering, when you change your coordinate system, how do you choose which is the best coordinate system? Is it through trial and error, or is it like there a process you follow?
It's a technical question. There is a way to do it. As you apply the algorithm for the Gram-Schmidt normalization when you are in algebra, there is an algorithm to do it in geometry too. So for instance, if you know that the space is flat, if it's flat, you would try to determine what I call the gradient symmetry, the gradient Killing vector. The gradient Killing vector are functions. So they give you, in normal coordinates, are the translation symmetries, the three symmetries in Cartesian. So if you find these functions, you can easily apply, you can easily find the transformation. So you just say this function is y, this is x, this is z, and that gives you the transformation. For other systems, it's a little more complicated, but if you have the algebra, you can do it. I mean, you linearize the algebra. You write the canonical transformation for the algebra.
Thank you.
Any more questions? Yingxia, I knew I could count on you.
So you said Einstein equation will be modified by incorporating this quantum effect, but I don't see it. Can you show that equation?
Okay. For instance, I can start from the Wheeler-DeWitt equation for the CDM. Is this one? This is this. If you take the equation of this is equation of motion for the cold dark matter. This constant here, this is a constant. Pu and Pv is constant, are related to the constraint. Are constrained by the energy density of the cold dark matter.
Yeah, but this is not a tensor equation. This is not for the space.
This is a
curvature.
It's not in terms of tensor. All the field equations in the mean superspace description.
Yes, this is only a particular case. It's not comparable to Einstein equation.
But you can write the Einstein field equations in this case, yes.
Well, this is only a particular case. It's not a general.
It's not the general equations. I didn't talk about the general equations.
Yeah, there's a question just behind Yingxia. Mesias, please.
Thank you for your talk. Can this methodology apply to stochastic differential equations?
I suppose why not, but I don't know. Probably yes. I mean, the idea is to transform everything to a geometric description. So
yeah, it would be interesting to see how, because stochastic processes are widely applied in either in finance or look at how you can apply this technique in different contexts.
it could be, yes.
Yeah.
Donovan, there's a question just behind Mesias.
Hi, thank you for your talk. So when we're looking at the Amarkov-Penny equation then, so it would just be the models that would reduce then to the second order structure that these results would be applicable to, correct? The models, that is. So like it would just be cosmological models, not necessarily all like gravitational models.
No, it can be anything. I mean, it can be any equation that can be reduced there.
Only in that case, only to the second order, right?
In this analysis, yes. But
So I suppose like if you take something like f of r gravity, which would be to power 4.
yeah, okay.
You
You
can do scalar tensor.
Actually, is the following. In FR gravity, since you can apply Lagrange multiplier to reduce it to second order differential equations, to scalar field descriptions, Brans-Dicke theory.
Yes.
That means,
yeah.
then yes. And because for FR gravity, the power law FR give you that approach. It's linearizable for the power law FR.
Yes, but probably not EGB. I'm not sure.
For Einstein-Gauss-Bonnet,
Yeah.
no.
Yeah, no.
But for FQ or for other scalar tensor theories, it's applied. I mean, the idea or the criterion is to the equations to be invariant under this set of algebra, the D cross T2.
Here, please.
Hi, since you produce these linearized equations, does that give you a way to get a hold of, say, some perturbative approaches eventually?
Perturbative for the only thing that I can say is that either if, for instance, if I have a potential force which not belongs, let's say, on these families, and it's not linearizable. However, when we are going to the system, we can't, when we perturbative around linear equations. So we can omit terms in the perturbation theory. So yes, that's a nice point, actually.
Do we have questions from the online audience, René?
Okay, we have one.
Yes, please, Donovan.
Okay, so I think it's asking whether you've tested these analytical solutions on actual data. So I'm going to read the verbatim for you. Are there any data tested to these solutions, like from astro or cosmological surveys?
The solutions that I presented are well known. I mean, we have the Schwarzschild solution. It's a static solution. They are not new. I haven't presented any new solution here, so they are already known in the literature and well tested.
Please.
I just want to clarify something from your discussion with Professor Ma. In the abstract, it says that the results are applied to explore the common solution space of general relativity. Then your remark to Professor Ma's question was that you don't consider the general equations in full generality.
Yes, I don't discuss all the equations. I select criteria. I mean, the criterion is the models that I discuss are models with which are they have a mini superspace description. I mean, I didn't discuss either for Kerr, the exact solution. So they are field equations of ODEs, and the solutions that we know they have this property. They have the common algebra. They're related like that.
And so do you think this work can generalize to
I don't
tensor
know.
equations?
To the tensor equations, the tensor formally. So in general, I don't know. I'm not sure. But if there are properties in other models, I mean, in the case where the Einstein field equations are PDEs, it could be. But I'm not.
Thank you.
Okay, if there are no more questions, then we just have to thank the speaker. Yeah. And Andronikos, as a little thank you, let me give you a copy of our famous Visarco magazine. Yeah.
Thank you.
Thank you very much. And Donovan is taking a photo.